All right, let's talk about something that's literally all around us, keeping our entire world moving, but we almost never see it. It's the science of lubrication, the invisible hero that makes sure everything from your car's engine to a giant wind turbine runs smoothly instead of just grinding itself into dust. This entire field of science really boils down to one huge fundamental challenge, a battle that engineers have been fighting for centuries. How in the world do we defeat friction? It's this universal force that's always there trying to wear down, heat up, and basically destroy every single moving part we invent. And the stakes are incredibly high. I mean, imagine a world dominated by friction. It's a world where things just break down constantly, where energy is wasted, where everything is inefficient and slow. But then there's our world, a world with lubrication. And that's how we get durable machines, incredible efficiency, and the mind-blowing speeds we rely on every single day. Okay, so how do we actually win this fight? Well, like any good journey, we need a map. And in the world of tribology, which is the fancy name for the study of friction, wear, and lubrication, our map is this really elegant and powerful tool called the Stryback curve. So what exactly is this Stryback curve? Don't let the name intimidate you. Think of it as a playbook or a cheat sheet for friction. It shows us exactly how friction behaves as parts speed up, as the load changes, or as the thickness, the viscosity of the lubricant between them changes. It's got this classic U shape. Now, here's all you really need to know to follow along. The up and down axis, that's friction. Higher up means more friction. Simple enough. The side-to-side axis, well, it combines a few things, but for our trip today, just think of moving from left to right as our machine getting faster and faster. This U-shaped curve really tells a story, a journey in 3 distinct parts. Researchers call them regimes. We start in a really rough place that I like to call the grind. Then we move through a transition phase, and our final destination, the sweet spot, is the float. So let's take this journey step by step. Our first stop, we're way over on the far left side of the curve where friction is at its absolute worst. This is the boundary regime. Just picture an engine the very moment you turn the key on a cold morning. Everything's moving slow, the load is incredibly high, and the conditions are just brutal. In this state, the film of oil is just way too thin to completely separate the two metal surfaces. If you could zoom in with a super-powered microscope, you'd see that even the smoothest-looking metal is actually a mountain range of tiny peaks. And here, those peaks, they're called asperities, are literally smashing and grinding against each other. This is where the vast majority of wear and tear happens. And here's the really crucial part. In this zone, the oil's thickness, or its viscosity, isn't the most important thing. What really matters are the properties of the metal surfaces themselves and, even more importantly, the chemistry of the oil. The pressure here is so intense that it can actually bend and deform the metal. So if the oil film itself can't do the job, how does anything survive this grind? Well, this is where the chemical engineers become the heroes. Modern lubricants are packed with these amazing additives. You'll see acronyms like ZDDP or TCP all over the research. These molecules are brilliant. Under all that heat and pressure, they react with the metal to form this tiny sacrificial shield, a tribofilm, that becomes the last line of defense, wearing away so your engine parts don't. Okay, so our machine is starting to pick up speed. We're beginning to slide down that U-shaped curve, and that brings us into our second regime, the transitional state of mixed lubrication. As you can probably guess, things are starting to get better here. So what's happening now? Well, as the parts move faster, they start to act like little pumps, dragging more and more oil into the gap. This action creates pockets of pressurized fluid that literally start to lift the surfaces away from each other. It's this weird hybrid state where you still got some of those little peaks grinding, but now the fluid is starting to carry some of the load too. This chart shows it perfectly. The total load is now being shared. Some of it is still carried by those solid-on-solid contacts, but a bigger and bigger slice of that pie is now being supported by the pressure of the fluid film. And that is why the friction starts to fall so dramatically. This mixed state might seem complex, but it's incredibly important in the real world. Why? Because most machines are constantly speeding up and slowing down. The research is clear. If you want to understand what's really happening during dynamic events like an engine starting up, you have to accurately model what's going on in this hybrid zone.
And here we are. We've arrived at our destination. As our machine continues to speed up, we glide right into the bottom of the Strybeck curve. This is the promised land of lubrication, the most efficient state possible. It's called hydrodynamic lubrication.
You know, the best analogy for this is a car hydroplaning on a wet road. The tires are moving so fast that they're literally floating on a layer of water, not touching the asphalt. It's the exact same principle here. The speed is high enough to force a continuous, pressurized wedge of oil between the two surfaces, completely separating them. There's no more metal-on-metal contact. They are floating on a film of oil. Now, this isn't magic, it's pure physics. The science that describes this whole phenomenon is governed by the foundational Reynolds equation. Just about every serious study on this topic, from jet engine bearings to artificial joints, uses some form of this equation to figure out how that load-bearing pressure gets generated in the fluid. It's the bedrock of the whole theory. And the result of getting to this state? It's a massive victory against friction. As this simple chart shows, the friction in this hydrodynamic regime is incredibly low. We're talking an order of magnitude lower than where we started back in the boundary regime. This is peak performance, peak efficiency.
And the science gets even deeper, believe it or not. In really high-pressure situations, like what you'd find between the teeth of a gear or inside a ball bearing, the pressure can become so extreme, hundreds of thousands of pounds per square inch, that it actually causes the solid steel surfaces to temporarily deform. That specialized field is known as elastohydrodynamic lubrication, or EHL for short.
So, we've made the complete journey along the Strybeck curve, from the harsh grinding of startup to the smooth floating at high speed. We get it now. But what does the future hold for this unseen science? Where do we go from here? Well, the next huge leap is from passive to active lubricants. Think about it. The oil in your car is passive. Its properties are fixed. But research is pouring into smart fluids. For instance, magneto-rheological lubricants can change their thickness in real time with a magnetic field. That means you could have active, on-demand control over friction. It's a total game changer. This is really just the latest step in a very long story. For thousands of years, we used basic animal fats. Then came the 19th century and petroleum-based oils. The 20th century gave us amazing synthetic oils and all those chemical additives we talked about. And now we're firmly in the era of nanomaterials and smart fluids. And the cutting edge of research is truly fascinating. I mean, scientists are exploring things like nano additives, graphene for instance, that act like microscopic ball bearings. They're perfecting lubrication with films of gas for things moving at incredible speeds. They're even engineering high-performance, eco-friendly biolubricants from things like sunflower oil. The innovation is just off the charts. And all this brings us to one final big question. As our technology keeps pushing into more extreme environments, getting smaller, faster, hotter, the war against friction only gets more intense. The challenge never really ends. So as we continue to engineer the future, you have to wonder, what will the next great lubrication frontier be?